In this video, we're going to talk about how to linearize data in a way, whatever this linearizing process is, it's going to enable us to get an equation for a nonlinear relationship. So we're going to be in math land for this, because that way we don't have to worry about units and sig figs, which I don't really want to worry about anyway right now. And I want to start out with my little secret. Okay. Whoops, there's a little problem with my little secret. It's actually y equals 2.5x squared. Sorry about that. Y equals 2.5x squared. Okay, in my little secret, I already know the equation for what we're going to do. We're going to pretend like we don't know what it is, but I just want you to know that this stuff is based on a math equation of y equals 2.5x. Okay, now I want to put that out of your mind and just say, look, you come across this table of values, not a data table because this is math land, it's just a table of values, and you decide I want to plot it to see if I can figure out what the equation is behind this data, or values. And so you plot it on a graph, and you see these points, and I don't have the guts to draw this best fit curve in pen, so I'm going to do it in pencil. I'll be right back. Okay, close enough. This is one of the reasons why drawing nonlinear graphs by hand is never easy, because that is hard to do. But anyway, I recognize the shape. I clearly recognize the shape. That y is going to be proportional to x squared, but I want the equation for it. I want to know y equals some constant of proportionality is called times x squared. Okay, again, you don't know that. So what we're going to do is we're going to linearize these values so that they turn out to be a straight line. So I don't have enough room here, so I'm going to start a second page. I'll be right back. Okay, time to linearize. I know you don't even know what that process is yet, but we're going to get a straight line graph out of this. Problem is, we can't change this relationship. Okay, there is a set relationship between the x value and the y value determined by my secret equation. And we can't mess with that. So we have to preserve that relationship while somehow getting a straight line graph that we can then use to come up with an equation. All right, and the key thing is for us to recognize that the one thing we do know is that y is proportional to x squared. And I'm just going to go ahead and do the process instead of trying to explain the process. So if you have a relationship on your original graph that suggests that y is proportional to x squared, and this is screaming this relationship, there's no doubt, then what you want to do is you want to make a graph of y, and here's the crazy thing, you want to make a graph of y versus x squared. Yes, we can do that. So on our graph, our dependent variable is y, and our independent variable is x squared. Yes, you can put x squared here. It is illegal. No one will come to arrest you. The math police said, I've checked it, they say it's totally fine. So your y column is going to be exactly the same. So we're just going to copy 0, 2.5, 10, 22.5, and 40 can be exactly the same, because it is exactly the same. It's y over here, it's y over here. Now this is x and this is x squared. So what we're going to have to do is, when we bring this value over, we're going to have to square it. So 0 squared is 0, 1 squared is still 1. Here we go, now it gets exciting. 2 squared is 4, 3 squared is 9, 4 squared is 16. This is our linearized. I know, so how do I know it's linearized? Well, you're going to see it, but this is what we call it. So when I make reference to, you need to have a linearized data table for this scenario, you're going to make a graph of whatever your input. So when we talk sciencey, this would be our input, and this would be our output. So that's what you do. Now what I'm going to do is let's plot it, and you will see the magic of linearizing. So my x squared, notice that this is x squared, it's not x. The values are going to go 0. Okay, Sorry, I'm not, don't do that. But my scale has to go to 16, so this has to go to 16. 2, 4, 6, 8, 10, 12, 14, 16, getting kind of tight in there. My y-axis doesn't change at all because the y variable didn't change. So this is going to be 10, 20, 30, 40. I'll say that one more time because that's important. The y is exactly the same. It's the x that is now weird. And I did cram this into a tiny space. All right, now we're going to plot these points, and we're going to see something interesting. So 0, 0. All right, 1 here goes to 2.5. 4 goes to 10. 9, halfway between, goes to 22. So 9, there's 20, 22.5 goes right there. And I think you're seeing a pattern here. And 16 goes to 40. That one doesn't look, that one's, did I do that one right? Anyway, I made my point. Let me check that one because it's like 9. No! That's 22.5. Okay, forget that guy. That's the problem. All right, what do you see? I see points that line up in a line. And so what we're going to do is we're going to draw a line of best fit. And there you go. So this original data, when we do this funky little linearized data table, creates a straight line. Now, you're very good at creating straight lines. Coming up with equations for straight lines. So we're going to need to get the slope. So let's get the slope. Okay, so basically I've got a run of 16 and a rise of 40. So the slope is going to be a rise of 40, no units, this is math land, divided by 16. I put that in my calculator, and I get 40 divided by 16 equals 2.5. The slope is 2.5. All right, the y-intercept is 0. So here's the equation for my line. Y equals 2.5. But here we go. You have to put this variable. You can't just put x because your quote-unquote x-axis isn't the x-axis. It's the x squared axis. So you get y equals 2.5 times x squared. So this is, I know the equation for this, but more importantly, if I go back to my original graph, which I was sitting there going like, I don't know what the equation is, you actually do when you follow this technique. So the equation for the linearized graph is the equation for the original graph. I'll say that one more time because that's the entire point of going through this process is you want to get the equation for your nonlinear graph. You do this linearizing process, you create this second linearized graph. Because you're good with lines and slopes and intercepts, you come up with it. You remember this is x squared, not just x. And then the whole point of doing this is to say, this equation, the equation that produces this line is y equals 2.5 times x squared. And guess what? You discovered my secret. This process is called linearizing the curve or linearizing the data, etc. In the next video, we'll talk about what to do when you have other nonlinear graph shapes.